Hi everyone, today we're going to continue our conversation on the inverse matrix of a square matrix. So last time we talked about how the inverse matrix is kind of like the multiplicative inverse of a square matrix. So today we're going to talk about how to find one of these, and we're specifically going to focus on doing it for a 2 by 2 matrix. So let's take a look. So we have a formula here, finding an inverse of a 2 by 2 matrix. And so there's a couple of things going on here. First off, we have this coefficient in front, 1 over AD minus BC, and I'm hoping this calculation looks familiar, where we multiply AD, and then we multiply BC, and we subtract those. And again, like I said, hopefully it looks familiar because that is how we calculate the determinants of a a 2 by 2 matrix. So we take basically the reciprocal of the determinant, and then we multiply that by a special version of our matrix where we flip-flop the elements top left and bottom right. A and D are getting flipped, and then in the other diagonal, B and C, those get multiplied by -1. So let's see this in action. So here's example 1. We have the matrix 4, -4 in the first row, 2, 3 in the second row. So if we go ahead and first off find the determinants, right? So again, this is just going down the diagonals. So 4 times 3 gives us 12, and then 2 times -4 gives us 8, but double, because it's double negatives, so we get 20, okay? And so we're going to take that value, and we're going to take its reciprocal, and then we're going to multiply it by a special version of the given matrix. We flip-flop the elements in the top left to bottom right diagonal, and then in the other diagonal, we multiply both of them by -1. And now it's just a matter of distributing and simplifying, and so we get a very odd-looking answer, but it's a bunch of fractions, right? 3/20ths and 1/5 in the first row, -1/10 and 1/5 in the second row. And again, this is just distributing, right? Basic matrix operation. And this matrix is the inverse of the original matrix. How can you prove that? Well, if it truly is the inverse, then I should be able to, I should be able to multiply these together, right? And so if I go first row, first column, that should give me a 1. If I go first row, second column, that should give me a 0. Second row, first column should be a 0 as well. Second row, second column should be a 1. What am I talking about, of course? The identity matrix for a 2 by 2. And so you can multiply these right out, and you will get the identity matrix, right? And you gotta combine some fractions, get some common denominators, but everything works out. And if you go ahead and do it the other way, it still works out. So you truly know they are inverse matrices of each other. Okay, let's do another one. Example 2. We have the matrix -3, -2 in the first row, 6, 4 in the second row. And again, we're going to start off by finding the determinant, and we're going to notice something, that the determinant ends up being 0, right? And so what's the reciprocal of 0? Well, that means I'm dividing by 0, which means this is undefined, and therefore this matrix does not have an inverse. Okay, last application of inverse matrices is to solve a system of equations. And so like we talked about with Cramer's rule as well, this is not your technique you would choose if the question was, on a standardized test, right? Find the inverse, or excuse me, solve the system of equations, right? You would pick substitution, elimination, something a little faster. But let's talk about how this is going to work. So the first thing you're going to do is you're going to break up this system into 3 matrices. And so you have a matrix that is the coefficients, right? And so again, this has to be lined up. X's in the first column, Y's in the second column. It has to be lined up. Then you have a variable matrix, and then you have the, kind of like the equation matrix, right? Like whatever numbers you have on the other side, okay? And so these first two matrices, remember, these are multiplied together, right? And so how do I get my variables by themselves? I would have to divide, except I can't really divide, right? But remember, dividing is the is the inverse of multiplying, right? And so to get this xy, this variable matrix by itself, what I'm going to do is I'm going to say, okay, on the, technically on both sides of this equation, right, I'm multiplying by the inverse of this matrix right here, which cancels it out on the left side. So I just get xy. And then for these numbers, this is going to get multiplied by the inverse of our coefficient matrix, the 1, 3, 2, negative 1. So we have to now find the inverse of this matrix in order to then multiply it by this one. Okay, so let's find the inverse. So the first thing I'm going to do is determinant again, right? And so hopefully by now we're getting pretty confident, right? Finding the determinant, multiplying the diagonals, we get -7. And so now we are going to go ahead and multiply. So again, we take the reciprocal, and then we're going to multiply it by, again, the top left, bottom right diagonal. Those get switched. The other diagonal, you multiply them both by a -1. And now we're just distributing -1/7 into all of these to get our inverse. And so, again, the inverse of the coefficient matrix is right here. We're going to plug it in so that we can multiply it by the -12, 11 matrix. So that's going to be my next step. Okay, so went ahead and plugged it in. Now matrix multiplication. And some of you might be wondering, like, hey, how come you have it set up this way? Remember, you have to go ahead and multiply in a certain order in order to get a solution. So this is a 2 by 2 times a 2 by 1. So remember, these middle numbers have to match, right? And then the outer numbers tell you what your solution is. And I'm glad that the outer numbers are a 2 by 1 because that's what this variable matrix xy is. And so we can go ahead and set this up, okay? And I'm just showing my work here, right? So, 1/7 times -12, right? 3/7 times 11, right? Add these together, you get 21/7, which is 3, okay? 2/7 times -12, -24/7, -1/7 times 11, add them up, -35/7, which is -5, which means that my solution is the ordered pair 3, -5. Okay, so again, would this be your first choice in solving a system of equations? No, but again, why do we learn these techniques? Because these techniques are scalable. You can apply this logic to a square matrix of any dimensions. Okay, that's all we have for this time. I'll see you guys later.